Today we're going to talk about vibration basics, spring rate, natural frequency, transmissibility, damping, and a sample problem. Vibration basics. When we talk about vibration basics, the first thing we talk about is spring rate. Spring rate is the force required to induce a unit deflection of a spring. A steel spring has a very linear relationship between force and deflection. Elastomeric springs or isolators may or may not be linear depending on the amount and direction of the load. Nonlinearity can be designed into elastomeric springs to achieve certain desired results. Elastomeric springs also differ from steel springs in that their stiffness is sensitive to the rate or speed of deflection. If an isolator or rubber spring is deflected quickly, it appears stiffer than if it is deflected slowly. Single degree of freedom systems. Vibration is an oscillatory motion. Any body with mass and elasticity can vibrate. The simplest type of vibrating system is called a single degree of freedom spring mass system. The spring is characterized by spring rate or stiffness K, usually given in pounds per inch or Newton per millimeter. It is also called a single degree of freedom system because the motion can occur in only one direction. In our example, this would be vertical. When a mass M is attached to a spring with a spring rate K, the mass moves to its position of equilibrium. The difference between the spring's undeflected free length and its position of equilibrium is called the system's static deflection, or D-stat. If a force or deflection is applied to the system and then removed, the spring mass will vibrate. When plotted against time, the position of the mass relative to its position of equilibrium is a sinusoidal curve. The maximum single amplitude is deflection of the mass from its position of equilibrium to its maximum displacement in one direction. The double amplitude displacement is the total deflection in both directions. The period or amount of time to complete one cycle is the time it takes for the mass to move from its equilibrium position to its peak in one direction, its peak in the other direction, and back to its equilibrium position. Frequency. Frequency is the number of cycles that occur in a unit of time. It is typically measured in cycles per second, also known as hertz. In this example, we may have a motor running at 3600 RPM, divide by 60, and you get 60 hertz. The natural frequency. If a load or deflection is applied to our simple spring mass system and then released, the mass will vibrate at a constant rate. We call this condition resonance, and the vibration rate is called the natural or resonant frequency. Natural frequency, Fn, is given by the formula 1 divided by 2 pi times the square root of k over m. This is always measured in cycles per second or hertz. For convenience, the equation for natural frequency can be written in many different forms, including natural frequency is equal to 3.13 times the square root of k over w, when k is given in terms of pounds per inch, that's the spring rate, and w is in pounds. The frequency will be in hertz. Transmissibility in an undamped system. So far we have talked about free vibration. What happens when a force or deflection is applied and then removed from the spring mass system? Now we will look at the system's reaction to a forced vibration. When deflection or force or acceleration is applied to the spring mass system as a sinusoidal vibration, the output through the system can be defined in terms of transmissibility. Transmissibility, or T, is equal to the output over the input and is dimensionless. Vibration output and input may be measured as motion, force, velocity, or acceleration. The transmissibility of a rubber spring is a function of the relationship of the input frequency to the natural frequency and the amount of damping in the elastomer. Transmissibility, or T, is equal to 1 divided by the frequency ratio squared, which is Fd divided by Fn, and that quantity is -1. For an undamped spring, when the forcing frequency ratio, Fd over Fn, is equal to or greater than the square root of 2, where Fd is the input or disturbing frequency and Fn is the natural frequency. The transmissibility curve. Here we see a transmissibility curve plotted against the frequency ratio. When the input frequency is very low compared to the natural frequency, the transmissibility is close to 1. When the input frequency is close to the natural frequency, the transmissibility is very high. Sometimes these numbers can exceed 12 to 14 amplification. This is the output is much larger than the input. When the input frequency is high compared to the natural frequency, the transmissibility is very low. The output is much smaller than the input. Usually, this is the goal of an isolator spring design. We wish to attenuate a disturbance of a particular known frequency. From the desired transmissibility, we can define the required frequency ratio and calculate the system natural frequency. Then, using the natural frequency calculations, we can calculate the required spring rates for our elastomeric springs. Transmissibility is the ratio of output to input. In this demonstration, my hand will be the input, the spring, metal spring will be the isolator, and the mass, M, is 1 pound. In this demonstration, I will show transmissibility of 1. Input and output are the same. 1 input in my hand is giving the mass 1 input. The next part of the curve is transmissibility and resonance. So you could see a little bit of input in my hand, and the spring mass is exciting the mass quite a bit. So it's amplifying the input that I have here to the mass is getting amplified. If the input increases, you could see that the mass is isolated from the input here. The mass is relatively constant and not moving. That's the desired output of an isolator, whether it's a metal spring or a rubber isolator. Again, 1-to-1, transmissibility at resonance, the mass is bouncing quite a bit, and isolation, where the mass is being isolated from the input. Dynamic deflection. No spring mass can completely isolate a disturbing vibration. Depending on the transmissibility, a certain amount of motion will occur at the mass. This motion is called dynamic deflection, or D sub D. It is calculated as double amplitude deflection with a total deflection in both directions. A base excited system. Vibration can be attenuated in a spring mass system in 2 ways. In a base excited system, the input is applied to the spring, and we are concerned with the output to the mass. An example is a sensitive electronic system, the mass, M, which is suspended on rubber springs or mounts attached to the deck of a ship. The ship deck transmits engine vibrations and other inputs to the springs. We want the springs to transmit a smaller, non-damaging level of vibration to the electronic system. This is a base excited system. The other system is a mass excited system. In a mass excited system, the mass itself is vibrating, the input, and we are concerned with the output to the base. For example, a vibrating air conditioner may be suspended on isolator springs to keep it from transmitting vibration to the floor of a building. In both cases, transmissibility is measured the same way, as are the calculations for natural frequency. Damping. An elastomeric spring has another characteristic that a simple steel spring does not. It has hysteresis damping, capital C. When elastomeric material is deflected, some energy is converted to heat. Without damping, a spring mass system will continue to oscillate at its resonance frequency for a long time after the input has stopped. With damping, the oscillations decay more quickly. Damping also has an effect on transmissibility, which we will discuss later. In the diagram, damping is shown as a dash pot, or C. The effect of damping on transmissibility. Here, transmissibility is plotted for 2 different levels of hysteresis damping. You can see that the greater amount of damping, loss factor, N, the lower the transmissibility at resonance. For frequency ratios above the square root of 2 in the isolation region, the amount of damping does not affect transmissibility. A loss factor of approximately 0.1 would be typical for resilient elastomer like natural rubber or neoprene. More highly damped elastomers like silicone could have a loss factor from 0.25 to 0.7 or higher. If the disturbing frequencies are known and adequate sway space is available, a lightly damped mounting system with a natural frequency well below the disturbing frequency would be selected. But in cases where the disturbing frequencies are numerous, unknown, or impossible to avoid due to sway space limitations, a highly damped system is preferred. The high damping reduces the peak response that can occur if some disturbances are near the natural frequency. However, other performance properties may be compromised. This is a demonstration using 2 elastomeric balls. One is natural rubber, the black one. The brown is a silicone, highly damped material. I will drop these on the tabletop and you will see what happens. The natural rubber ball bounces very high because it has low damping. The silicone ball is pretty dead and doesn't bounce. Elastic shear modulus. In order to design elastomeric springs with desired stiffnesses, we must know the static and dynamic stiffness characteristics of the elastomer. Elastic shear modulus, G, is the ratio of stress to strain. It is a measure of stiffness independent of geometry, similar to Young's modulus, E, which is a tension modulus commonly used to describe metals. The so-called static shear modulus, G, is measured at a very slow rate of strain. When elastomers are sheared more quickly, there is a time lag or phase angle between the deflection and the resulting force. Dynamic shear modulus, G star, can be described as a complex number with an elastic shear modulus, G prime component, and a damping shear modulus, G double prime component, and a phase angle delta. The ratio of damping modulus to elastic modulus, or tan delta, is also called the loss factor. The transmissibility of a rubber spring at resonance is approximately equal to the inverse of the loss factor. Damping terms for the loss factor. Eta, or loss factor, tan delta is also one that's used. C over C sub C is the fraction of critical damping, or zeta, which is also the C over C sub C, or fraction of critical damping. Modulus. Shear modulus of elastomeric materials varies with strain, strain rate or frequency, and with temperature. Since damping is a function of modulus, it is sensitive to the same conditions. That's why it is very important to know the exact condition under which an isolator has been tested and the conditions which it will see in the application. Elastomers. There are several different types of elastomers that can be used in isolators. Natural rubber is the most common, as is neoprene. Natural rubber has very high tensile properties and very resilient and gives good fatigue life. Neoprene is oil resistant in some cases and does well with fatigue life also. There's also chlorobutyl, polybutadiene, silicone, which is one of the highly damp materials, and several other specialties. TPEs are thermoplastic elastomers that can be reprocessed. Applications. We have a problem where we need to isolate a disturbing frequency of 60 Hertz, and we desire an isolation efficiency of 90%. We need to find the natural frequency in the static deflection that's required to meet those objectives. So we're going to calculate transmissibility. Transmissibility is, again, the ratio of output to input. So if we have 100% minus the isolation efficiency of 90, divided by 100, we need transmissibility of 0.1. Now we can calculate the natural frequency from the formula T is equal to 1 divided by the frequency ratio squared minus 1. We want to solve for Fn. We know Fd, which is 60 Hertz. We know transmissibility of 0.1. If we plug those in the formula, Fd, which is 60, divided by the square root of 1 divided by T, 0.1 plus 1, calculation is 18 Hertz. Solving for Fn, we can calculate the static deflection, which is 9.8 divided by the natural frequency squared. In this case, it's 18. 9.8 divided by 18 squared. The static deflection required of the isolator is 0.03 inches. Thank you. That concludes vibration isolation.